Now we're going to talk about collections. There's almost no need for a formal definition here, since a collection is, as the name implies, just a group of things. You could have a collection of books, a collection of Udacity employees, or even a collection of desk animal things that I talk to when I'm stuck on programming projects and the coaches aren't around. Let's make a few observations here. Collections don't have a particular order. You could shuffle some elements around and it wouldn't make a huge difference. Similarly, we couldn't say, give me the third element in this collection, since there's no inherent order. Collections also don't need to have the same type of object. Everything in the room could be in the Around the Udacity Office collection, even though there are books and people and animal things. A collection on its own really isn't something you can use in a programming language. However, there are many data structures that are extensions of collections, so they just add more rules to the ones that already apply for collections. Let's take a look at some of those now. A list has all the properties of a collection, so it has a group of things, but the objects have an order. A shopping list, while not really something programmers deal with a lot, happens to have a lot of the same properties as the list we use. There are things that might not have the same type of object, but they're still related to everything else on the list. The order doesn't mean much, it's just the order that I ran out of each item. And there's no fixed length. I could just keep adding things to the end, or adding and removing from the middle, and it doesn't really affect anything. Again, what exactly the implementation looks like for adding elements will change based on the language and the type of data structure. We're still talking theoretically here, so don't sweat the details too much yet. In this lesson, we'll explore several types of lists. Different programming languages treat them differently. Sometimes a list is incorporated as a core feature of a programming language, but what that looks like can vary wildly. The videos here will talk about the theoretical concepts that could apply to any language, while the text will explain the language-specific implementations. Arrays are perhaps the most common implementations of lists. In many programming languages, the ability to create an array is built in as a core feature. You may have seen or heard of them before, but it's important to have a more formal definition of what an array is so we can compare them to other data structures a bit later. As I mentioned before, an array is a list with a few added rules, so we already know that it has some things in some order. In some languages, you can only have objects with the same types in the same array. And in some languages, your array can contain different types, so we can't use that as a rule to define arrays. It would also be nice to say that arrays have a set size that you determine right when you create them. Again, this is only true in some programming languages, so we need to avoid adding that to our definition. Defining the thing that different languages call arrays is actually pretty hard. There is one big feature that differentiates arrays from lists. Each array has a location called an index. An index is just the number associated with that place in the array. It would make sense to number these boxes from 1 to 5, but of course it can't be that simple. Normally, an index starts at 0, so instead of referring to these boxes as 1 to 5, we usually say it's 0 to 4. Having indices can make using arrays a great, or sometimes terrible, choice for the code you're working on. If you need to access a certain location in the middle frequently, using an array can be a great choice. You just need to keep track of how long the array is, calculate the middle element, and check the object in the box with that index. Insertion and deletion can be really messy with arrays, though. Inserting in the end is often easy, but it can be hard if the array has a set size and you've already filled it up. Insertion is difficult if you want to put an element in the middle of the array. If you want to do a normal insert, you'll need to move everything after the inserted element back into different boxes with a different index. The operation as a whole is pretty inefficient since you need to move every element behind the one you're inserting back in the array. In the worst case, this operation takes linear time, or big O of n. Deletion causes a similar problem. If you delete an element, you have an empty box. You can't just look at the index and say that this is the fourth element anymore, since there's an empty box before it. Again, all of this can change based on the way a particular language implements an array, but it's important to consider when talking about arrays abstractly. Hopefully arrays are starting to make sense to you. Let's quickly look at them in another way. You can think of an array kind of like this. It's a set of boxes where each has an address called an index. This paper chain is more similar to a construct called a linked list. A linked list is an extension of a list, but it's definitely not an array. There's still some things that have order, but there are no indices. Instead, a linked list is characterized, well, by its links. Each element has some notion of what the next element is since it's connected to it, but not necessarily how long the list is or where it is in the list. An array is different. There's nothing in one element of the array that says, here's your next element. You know what the next element is by what the next index is. My first thought when I heard this was, why would anybody ever want to use a linked list? An array gives you more information since you already know where the next element falls in the array. However, as we discussed before, adding and removing elements from an array can be really complicated. Adding and removing elements from a linked list turns out to be so easy by comparison. You can actually just take an element out or add one in. There's only one real quick consideration here, but we'll talk about that in a minute. In higher level programming languages, there often isn't a distinction between linked lists and arrays. There's just a list that has the properties of both. However, questions about these two data structures are fairly common in interviews, so it's important to know the difference. Again, the main distinction is that each element stores different information. In both cases, a single element will store a value, or the actual information. So, if you have an array or linked list of numbers, the value will be a single number. If you have an array or linked list of string values, then each value will contain a string. In this case, we're just going to stick with numbers. Now, in both cases, we store one other type of information, but that type is different. In an array, we would store a number as an index. You can get the next element by querying the array for the element at index 1 in this case. Let's clear this out and focus just on linked lists for now. In a linked list, we store a reference to the next element in the list. In many languages, this will look like assigning the actual next element as a property of this element. Way down at the hardware level, your element actually has some space dedicated for it in memory. These are representing the memory locations. So in this case, the next component is actually storing the memory address of the next element, while this element is storing null because it doesn't point to anything else. The nice thing about this system is that it's pretty easy to insert and delete elements. Adding an element is going to look something like this. We really just need to change the next reference to point to the new object, and done! There's a quick trick you need to remember though. If you delete the next reference and replace it with a new object, you'll lose your reference to this object. You should always assign your next pointer for this element before you assign your next pointer for this element, so you don't lose your reference to this one down here. Now everything looks great. Note that insertion takes constant time in this case, since you're just shifting around pointers and not iterating over every element in the list. Removing an element is going to look pretty similar, so I'm not even going to go over that now. There's also something called a doubly linked list, where you have pointers to the next element and the previous element. The rules are pretty similar for a doubly linked list, except you can traverse the list in both directions now. Again, you need to be careful not to lose references when adding or removing elements, but it's easier than performing these operations on an array.
Albert Einstein reportedly said, "It's not that I'm so smart, it's just that I stay with problems longer." Your drive to stick with things and see them through, in a large part, will determine your success, not just with this nanodegree program, but in your job and in your life. Our goal at Udacity is to ensure that you meet your goals, so we're here to help you learn, like Einstein did, to tackle challenges and persevere through them. Our students come from all walks of life, and their goals are as varied and different as they are. But whatever your personal goals are, we have content, resources, and support mechanisms to make sure that you reach them. If you're stuck, or even if you just fancy saying hello, remember that your community is here for you. Students, mentors, and Udacity staff in your network are all cheering you on and want to help you learn as much as you can.